Clock controls the world, we control the clock. Small cheer and great welcome makes a merry feast. Good day to all the IEEE professional and student members. I warmly welcome you all on behalf of the Vehicular Technology VTA Society, IEEE Madras Section, to this wonderful session on self-evolving and transformation protocol architecture for 6G technology by Dr. Lin Cai, Professor, Department of Electrical and Computer Engineering, IEEE VTS Board of Governors of the year 2019 to 2024, University of Victoria, Canada. Now, I kindly invite Dr. S. Brinda, Chairman of VTS Society, Madras Section, to deliver the welcome address.
Yes, thank you, Vignesh. Respected Chief Guest Professor Lin Cai, Madam, respected Principal and IEEE Madras Section Chairman Dr. Purkumaran Sir, respected executive members of IEEE Madras Section, and student and faculty members from various colleges of Tamil Nadu and Puducherry, and my dear IEEE Madras Section VTS team members, fellow staff members, and my dear student members. A very good morning to one and all present here. On behalf of IEEE Madras Section VTS chapter, I take immense pleasure in welcoming all for this inauguration of this society. And the objective of this society is to give knowledge, explore knowledge about the theoretical, experimental, and operation aspects of electrical and electronics engineering in mobile radio, motor vehicles, and land transportation. So the concentration is on these three fields, and the exposure of the professional members of these three domains: mobile radio, motor vehicles, the communication parts of the motor vehicles, and land transportation is covered in this domain. And the society is promoting the objective through the leadership of its officers and members in encouraging and exchanging both the technical and professional information among the members of the society and other groups. And how this function is accomplished through this society chapters means by means of sponsorship, sponsoring technical conferences and seminars, and publications of technical journals and books in this respective field, awards of recognition for excellence, either for the chapters and student members or professional members, and participation in the development of standards. We are getting the chance through this membership and membership support activities. What are the activities related to this membership we are getting through this society forum. And in general, the society forum, any kind of society, is providing lifelong learning to update our technical skills periodically in the domain of our interest. So, and similarly, this VTS society was initiated during the year 1950s and exited, that is up to 1983, the only minimum members, around 2,000 members were present. And today, with the evaluation of wireless technologies, that is, the membership is all around the globe, is around 5,500 today, because everyone is interested in using the cellular technology. And so this field has come up with the new concepts and evaluation. And so this is one of the emerging field today we are talking about. And what are the latest technology we have, like the 4G, 5G, 6G, all the technologies we are trying to implement in the existing equipments, and then we are trying to get the we are trying to overcome the that is the disadvantages of those domains. So today, to inaugurate this society and to give insights on 6G communication, which is one of the emerging one, we are just stepping into 5G, and Madam is going to give a talk about 6G communication today. So we are very much honored to have our chief guest, Dr. Professor Lin Cai, from the Department of Electrical and Computer Science, University of Victoria, Canada. And she's also the Board of Governors of this Vehicular Technology Society from up to the 2024. And Madam, if you look at the profile of Madam, Madam received elected as member of Royal Society of Canada's College of New Scholars, Authorists and Scientists during the year 2020, and also received the award Star in Computer Networking and Communication by N2 Women. And His research interest areas are mainly focuses on communication and networking. So we as easy people or electronics and communication people, so the main area madam is working and doing lot of research in this forum. And also he madam involved in a lot of activities related to vehicular technology societies. And madam is the founder of Vehicular Technology Society for uh, um, Society of Victoria section, the hometown section, and elected member of IEEE Vehicular Technology Society Board of Governors for up to this 2024, and associate editor of IEEE Transactions on Vehicular Technology, and served as a DLP for IEEE VTS Society, and so on. So, lot of profile and roles Madam played under IEEE. BTS and Comcast Society. So we are happy to welcome you, Madam. Hearty welcome, Madam, to inaugurate this society. And I welcome our beloved Chairman IEEE Madras Section, Dr. Porkumaran sir, whose support and motivation is always instrumental in organizing events under his leadership. Welcome, sir. I also welcome all the Exiga members of IEEE Madras Section, and I am happy to welcome the team members of BTS Madras Section, and all the participants from Tamil Nadu and Puducherry for all very eagerly registered to attend this program. A hearty welcome to all the members. Thank you all. Now over to Vignesh Velappan.
Thank you, ma'am, for the warm welcome. Now I kindly invite Dr. K. Porkumaran, Chairman, IEEE Madras Section, to deliver the inaugural address. Please, sir.
Good morning to all. I'm audible.
Yes, sir. Yes.
The distinguished chief guest of today's inaugural function of Vehicular Technology Society, IEEE Madras Section, Professor Dr. Lin Cai, Professor of Department of Electrical and Computer Engineering, IEEE VTS Board of Governors, 1924, University of Victoria, Canada. The chairperson of IEEE VTS Madras Section Chapter, Professor Dr. Gupta, and all IEEE Madras Section EXCOM members. Somebody to mute some disturbances. Others can mute, please. I think host, you can mute others.
Sir, yes, sir.
Yes, thank you. Thank you. It's a great initiative from IEEE Madras Section and the committee members of Vehicular Technology Society of IEEE Madras Section for inculcating and inspiring the scientists, technocrats, student members, faculty, researchers in this specialized vehicular technology area. So at this juncture, on behalf of IEEE Madras Section, as a chair and IEEE India Council EXCOM member, I am warmly and respectfully welcome Professor Dr. Lin Cai from IEEE VTS Board of Governors, University of Victoria, Canada, for your kind presence and spending her valuable time for motivating all IEEE student members, faculty, and the professional members of IEEE Madras Section. I'm happy to inform that we have highest number of societies in IEEE Madras Section, and we have got a highest number of membership, and our students, faculty team, professionals, IEEE fellow members, they participated in various activities, especially during the IEEE Extreme event. IEEE Madras Section were in third position globally, and Sairam Engineering College student chapter was one among the top in global position of IEEE Extreme competition of 6.0. Like our professional members, faculty team, IEEE fellow members, they are contributing for the advancement of the scientific community. So at this juncture, I'd like to once again welcome Professor Dr. Lin Cai for this inaugural ceremony, and other members of VTS and all ex-com members of IEEE Madras Section for their wonderful contributions and presence during this inaugural ceremony. Thank you very much. Wish you all the best. Thank you.
Thank you, sir.
Thank you, sir. Now, I kindly request Mr. R. Srikanth, Treasurer of VTS Society IEEE Madras Section, to introduce our guest speaker of the day. Please, sir.
Thank you, Vignesh. Am I audible?
Good.
Okay. Thank you, ma'am. A warm good morning to one and all present here. It's my immense pleasure to welcome the chief guest of the day, Dr. Lin Cai. She is a professor of Department of Electrical and Computer Engineering at the University of Victoria. And she is an NSERC EWR Stakei Memorial Fellow and an Engineering Institute of Canada EIC Fellow and IEEE Fellow. In 2020, she was elected as a member of the Royal Society of Canada's College of New Scholar, Artist and Scientist, and 2020 Star in Computer Networking and Communications by N2 Women. Her research interest has been in several areas in communications and networking, focusing on network protocol and architecture, design supporting emerging multimedia traffic, and the Internet of Things. She was a recipient of NSERC Discovery Accelerator Supplement DAS grant in 2010 and 2015 respectively. She has co-founded and chaired the IEEE Victoria Section Vehicular Technology and Communications Joint Society Chapter. She is an elected member of the IEEE Vehicular Technology Society Board of Governors 2019 to 2024. She is the Associate Editor-in-Chief of IEEE Transactions on Vehicular Technology and has served as a distinguished lecturer for both the IEEE VTS Society and the IEEE Communication Society. It's a great honor to have you with us in today's IEEE Madras Section Vehicular Society inauguration, ma'am. Today, she is here to give a technical talk on self-evolving and transformative protocol architecture for 6G. The session is all yours, ma'am. Thank you.
Yeah, thank you, Mr. Srikanth, for the very nice introduction. And I would also like to thank Professor Pokomaran and Brindaha for your invitation. It's my great pleasure and honor to be here to witness this very happy moment of the new chapter begin here and to share a little bit of my own research experience with you. So may I share my screen?
Yes, ma'am. Yes, ma'am.
Okay. Yeah, can you see my screen?
Yes, ma'am.
Okay, good. Yeah, my talk today is about self-evolving and transformative protocol architecture for 6G. We know that since 2020, 5G cellular system standard has become like commercialized worldwide. Meanwhile, we are preparing for the next generation wireless technology because we know that each wireless generation typically lasts 1 decade. So now is probably the best time to work on the fundamental research issues for 6G. So first of all, we need to take a look what are the new challenges and the new opportunities for 6G network architecture and the protocols. Yeah, because my research is about network architecture and the protocol design. Yeah. So if we take a look for 6G, we know that from 1G to 5G, the current cellular network has already a very good coverage on the high population areas. However, because of in our Earth, 70% of the surface are water, and many places which is not so densely populated are still not covered by cellular system. So the current coverage of the whole Earth surface is only about 6 to 7%. So there's still many places without any cellular coverage. But in 6G aims to be a ubiquitous system to cover all lands, including rural, remote area, or islands, and also the depopulated zones. It will also have the coverage above and underwater, which corresponding to 70% of the Earth's surface. Furthermore, 6G will exploit altitude dimension with air and space coverage using UAV, drone, balloon, LEO satellite, MEO satellite, so on and so forth, and even go to deep space and other planets and moons. So the ubiquitous coverage all over land, water, air, and space relies on heterogeneous old and new wireless communication technologies with spectrum ranging from sonar, microwave, millimeter wave, terahertz wave to laser, and air photonics. The heterogeneous link with a very diverse physical media rely on different communication technologies and lead to very different link behaviors. Also, given the ubiquitous coverage, like we also find that 6G is associated with very different levels and types of mobility. For instance, UAV and AUV may have very arbitrary speed and movement. And the vehicles may have arbitrary speed, but the movement is confined to the roads or rails. And the satellites are moving in very high speed, but luckily the speed and the direction are quite deterministic. Okay. And we see these different links and different mobility patterns will lead to different link characteristics and different constraints for our network design. For instance, underwater have extremely low delay and very limited spectrum. And the UAVs in the sky have very limited energy supply. Millimeter wave, terahertz wave, and the laser have limited coverage, and they are very sensitive to weather and the environment. So the availability, reliability, bandwidth, stability, delay, and the other link characteristics and constraints often deviate from the current dominant internet communication systems, including 5G systems. Okay. When a flow traverses different types of wireless and wired networks, how to adapt to the new environment and ensure this end-to-end service is really an open and a very challenging issue. And meanwhile, from the applications perspective, 6G will support human, cyber, and physical interactions, enabling numerous new applications. Many new applications have very stringent quality of service requirements in different dimensions. For instance, AR, VR, hologram communications require very high data rate, and many cyber physical system applications require much higher reliability and very stringent on-time and in-time services, such as vehicle to everything V2X communication, industry controlled system, robot UAV SWAM. All these applications, they have very stringent delay and reliability requirements. Okay, and TCP/IP is the current protocol stack designed for our mainly human consumers. So our humans are very intelligent. We are quite resilient to delay, loss, and error. For instance, when we have internet IP phones. Even the IP phone lost 10% of the packets, we can still understand each other. But this is not the case if the receiver is machines or algorithms, okay? So in 6G, because of we needed to support this machine-to-machine, machine-to-algorithm, physical system to cyber system applications, this requirement in terms of delay, loss, jitter becomes much, much more difficult compared to support human-to-human communications. So in current TCP/IP network, our end-to-end protocols were mainly designed to efficiently and fairly share network resources. They have no mechanism to deal with things like throughput, delay, or jitter. So routers and switch, they don't know what users are asking for, and satisfy multidimensional QoS requirements is very difficult, if not impossible today. In addition, the new applications between human, cyber, and physical, they also require many new communication service modes. For instance, we will see like some multicast and broadcast applications such as mobile TV, video on demand. And so some cases we have multi-point to point cast, we call it in-cast. For instance, in sensor networks, crowdsourcing, federated learning applications. And we also see some multi-point to multi-point or group cast situation for like online gaming, robot UAV swarms, V2X, etc. Meanwhile, our TCP/IP protocol stack was designed mainly for unicast. They are challenged by this all kinds of cast. We use a wildcard star cast to represent all types of unicast, multicast, broadcast, incast, group cast, so on and so forth. So how can we support all these star casts, particularly leveraging the wireless broadcasting medium is an open issue. Finally, 6G should be intelligent. Traditional internet provide end-to-end data pipelines. Okay. In the new era of 6G, we anticipate that network will incorporate communications with storage, computing functions, and becoming a large-scale distributed systems supporting ubiquitous intelligence. In addition to data transfer, intelligent 6G network can also collect the data using sensing and signal processing, and store the data with caching content distribution system, and process data with various types of coding and compression technology, and even learn from data, applying AI for network management and control. And in addition to that, more importantly, like our 6G need to support, in addition to apply AI for network, our 6G network actually needed to support all kinds of AI. So our 6G needed to support various types of centralized or distributed learning or AI applications. But our TCP/IP protocol was designed for data pipe only, not for ubiquitous intelligence. Current networks do not have a built-in block to satisfy the intelligence demand systematically. Okay, given this 6G challenge, we summarized like ubiquitous coverage, stringent quality of service, darkcast, and ubiquitous intelligence. The existing internet architecture faces many issues and problems. The current TCP/IP protocol architecture has this kind of hourglass feature. On the top, there are all kinds of applications, and on the bottom, the communication link and the medium can be highly diverse. In the middle, we have very limited choices, which are transport layer protocols such as TCP/UDP and the IP network protocol. When new application requirements occur or new communication technology occur, we have to create new protocols or use tunneling to fix the problem. This design encounter many issues. First, TCP/IP protocol stack cannot guarantee end-to-end delay or throughput. There is no way to do that. Second, in the wireless domain, the link layer control and the end-to-end transport layer control often redundant, and sometimes they even conflict with each other, leading to resource wastage and performance degradation. Third, tunnel over tunnel leads to high overhead and performance degradation. Finally, the tunnel, which is particularly undesirable for this ultra reliable, low latency communication or machine-to-machine communication services due to the very high overhead and the very low efficiency, as well as lack of QoS support. So now let's move to 5G. Let's take a look at the current 5G network architecture and make an evaluation whether it can solve the 6G challenges we mentioned. We noticed that 5G mobile core is divided into a control plane and a user plane. This is an architecture feature called CUPS, control and user plane separation. This is quite similar to the data plane and the control plane separation used in software-defined networks, which has been deployed in like a data center types of scenarios. In 5G mobile core, control plane handles all signaling traffic, include UE user authentication, registration, mobility tracking, etc. They use the protocol of SCTP over IP to deliver this signaling traffic. Meanwhile, the mobile users' data, audio, video, text, etc., they use SCTP over IP. Sorry, they use a GPRS over IP. GPRS tunneling protocol, GTP over UDP over IP. This is handled in the user plane. Using this CUPS architecture, all control and management functions, such as AMF, this is access and mobility management function, SMF, session management function, so on and so forth. Okay, so all these can be implemented in software and hosted in the cloud. So in this way, the deployment of these control and management functions can be more efficient and more flexible. However, for high reliable and low latency services, 5G architecture still miss an important piece of issue, that still miss the capability of fast control to ensure faster reaction to service requirements and the network dynamics in sub-second time. So sometimes we need to have fast control decision to be made in millisecond level. And these types of fast control in millisecond level need to be associated with each data flow and each data packet. So it has to rely on communication protocols in the user data plane. So this is the thing missed in the existing 5G architecture. Therefore, to deal with all these 6G challenges, we conclude 6 need a new protocol architecture, which we proposed so-called self-evolving and transformative protocol architecture. In this architecture, each protocol can be assembled in real time using a wide range of control functions according to different applications, heterogeneous quality of service requirements, handle these starcast service modes, support ubiquitous coverage, and this new architecture aims to help 6G become an infrastructure for ubiquitous intelligence. Okay, to achieve so, this is our design. On top of 5G CUPS, user plane and the control plane separation, okay? And we take one step further. We divide this control plane, we further divide this control plane into three parts, okay? All these different parts have different control time granularity. Here, the right one, here the rightmost one is the user control, which handles control functions related to user associated functions such as billing, accounting, etc. And in the middle, we have this session control, dealing with session level authentication, policy rules, mobility, etc. And these two levels of control can take a relatively long time to handle. So we can move them to the cloud or sometimes in the edge servers. So this is similar to current 5G architecture. But the left part of the control plane, the blue one here, this is the flow level or packet level control, which needs to make control decision in very short time period in milliseconds. So it must be coupled with the data plane and be deployed inside the network. In this way, each network entity, no matter whether it's end systems or routers or switches, they should run a protocol control agent, which is a piece of code, a software that control, assemble, and confine the protocols for each entity. This is the intelligence we introduced inside the network. So with this protocol control agent, we call the PCA, it can enable in-network intelligence, and fast control decision can be made to deal with all the 6G challenges we mentioned. Based on this cubic data plane and control plane model we introduced, so the 6G system in general would work like this. Here, this yellow bar represents the user control. The green bar represents the session control, and the blue bar represents the flow level and the packet level fast control. When a user accesses this 6G service through the access node, okay, and the user control function at the access node can exchange information with the core network in the cloud, with this control function, user control and session control function in the cloud, hosted in the cloud. And similarly, the section control module can also be hosted in these clouds as well. And if some section needs faster control, the corresponding control function can also be pushed to the edge servers using edge computing capability there. On the other hand, the control protocol agent, which is the blue ones, they should be close to the data and the user plane. So all entities from the end devices to access network to router switch in the core, so on and so forth, they all need to have their own protocol control agent, the blue one here, okay, sorry. There. So this in-network intelligence enabled by this PCA can deal with all types of 6G challenges. Let's take a look how. Next, we introduce how we develop our so-called self-evolving and transformative protocols. In the traditional internet architecture, it either takes the one-fit-all approach without much concern on applications. For instance, we use IP protocol to solve all packets. And sometimes we also take a one-for-one approach by developing many new protocols for each new applications, okay, leading to very low efficiency and high complexity. Different from this traditional approach, in our proposed set protocol architecture, a set protocol, self-evolving and transformative protocol, It should be able to serve a large number of applications while considering their needs. To achieve so, the new protocol should take a modular approach, similar to our object-oriented programming. We can decompose the protocol control functions so protocols can be assembled and configured using different control algorithms and configurations to deal with different requirements and network dynamics. Let me give you an example. Here we use the transport layer protocol as an example. End-to-end transport layer protocol, for instance, TCP, needs to deal with 4 types of control: connection management, flow control, error control, and congestion control. In the current TCP protocol, it takes all these 4 coupled control together. So TCP can provide one and only one types of service, which is connection-oriented, reliable, stream service with flow and congestion control. Now we let all these control functions to be separated and to be decoupled. In addition, for each function, we can define different types of control algorithm or control mechanisms to handle that. For instance, for connection management, we can use handshake-based, like TCP3 handshake to establish connection, two-way handshake to release a connection. And we can also use some other approach, like using timer to set a connection or release a connection. For flow control, similarly, we can use window-based flow control like TCP, or we can use rate-based control. For error control, we can use ARQ type to use sequence number checksum and retransmission, or we can use forward error correction coding types of error control mechanism. For congestion control, we can use packet loss as the congestion signal, or we can use delay as the congestion signal and develop the congestion control accordingly. So we can see that now by decouple these 4 functions, by giving each function 2 choices, and we can turn off this, which corresponding to 3 different choices. Now we have how many combination? We have 3 times 3 times 3 times 3. We have 81 different combinations. Okay, these 81 different combinations will take different control blocks and provide different types of services. So we can see this is just a simple example. We can imagine for each types of control, the choices can be keeps on developing, and we can have more and more choices. So the possibility will grow exponentially. In this way, by decomposing the control functions and reassemble them flexibly, one protocol can provide numerous types of services. So this is what we want to achieve. Once we decomposed the control functions, the next important issue is how to assemble and configure these protocol control functions to satisfy all types of quality of service requirements and handle all types of network dynamics. Here, in the control plane, we mentioned that we need to implement a protocol control agent, which is to handle this challenge issue. This protocol control agent needs to interact with all protocols in the stack. For instance, here is an example in the end system. PCA can receive users' quality of service requirements and the transport layers measurement, network end-to-end service measurement, and the network and the link layers network measurement, as well as user location, mobility, so on and so forth. It can collect all this information from different places. And then it relies on various types of online or offline machine learning and AI algorithm. So it can make intelligent decision in pick the right control blocks and configure it appropriately to each protocols. For PCA to make protocol configuration decision, we can make it easy by defining some default configuration for as an easy start or for the like a menu for begin. And then the protocol configurations can be updated based on the real-time measurements and the feedback. So if the network operates very well and there is not much delay, jitter, loss, etc., the PCA can probably decide we can probably use less overhead in error control, for instance. And if the network becomes lossy or have certain issues, the PCA can decide probably it needed to enhance the error control or even use a multiple pass, multiple transmission and more redundancies, these type of things to improve the end-to-end performance, so on and so forth. So we can see this protocol configuration needed to be updated on real time based on this measurement and feedback from the network or from the acknowledgement. We note this decision-making by PCA is essentially a multi-armed banded problem, which has been heavily investigated in the literature. There are many existing tools, such as contextual banded reinforcement learning, to solve these multi-arm banded problems. But we believe this is an open research area worth further investigation because we needed to come up with the best strategy in very different environments for different applications, so on and so forth. So I think I welcome all the researchers and the students to think about it and to probably make your own contributions here. Okay, let me quickly summarize these new protocol architecture features. So this new architecture relies on in-network intelligence. So this PCA needs to be deployed in each network entity. It's not in cloud far away because the delay to and from the cloud is too long to make those fast decisions. Okay, and this PCA can take information not limited to those in traditional layered architecture. And these PCAs can collaborate with each other. They are intelligent. They can collaborate with each other to make intelligent decisions together. And this kind of distributed intelligence can react to channel or network or application dynamics very fast, more robust, and more efficient. These PCAs can choose control functions from a growing library, making our set protocols self-evolving. So when we have more functions coming in, these protocols can be even more flexible or have even more functions and provide more types of services. So this PCA can switch functions for a single flow when the service requirements or environments change. The protocols can be transformative in dynamic environments. Okay, yeah, sorry. We call it self-evolving and transformative protocol architecture. Yeah, I also want to mention that. Yeah. Okay. Yeah, we also want to mention this set protocol could be backward compatible with TCP/IP, which means in an environment, the majority of nodes only understand TCP/IP, do not understand the set. The new set protocol can try to downgrade itself and still use TCP/IP or what TCP/IP can handle to talk to each other. So this way, our set new architecture can be compatible and can be incrementally deployed. And of course, when more and more nodes understand this new architecture, the PCAs can negotiate with each other and support things like non-IP protocols or Starcast, so on and so forth, which is beyond what current TCP/IP can handle. Okay, so currently in my research team, we develop this new architecture and we apply this new architecture in 4 research issues. First is how to guarantee packet level delays, guaranteed services. So even in a single flow, different packets probably have different deadline or different delay requirements, how the network, how the routers to handle all these packets such that each packet can be delivered to its destination before its deadline. So this is the first research issue we work on. The second is we try to develop this user network collaboration using multi-path handoff. And today I will give a quick example about this. And the third research topic is about how to apply our new architecture to support various types of Starcast services with QS provisioning. And the last, we try to investigate how we can integrate sensing, computing, storage, and communication services, leveraging the advantage of our new architecture. And I will spend a few minutes to give an example. This is a case study, how we apply the new tech architecture to develop a so-called mobility-aware multi-path quick for satellite networks. Okay. So for mobility support, we found this multi-homing design is a promising direction. For a multi-homing host, it is equipped with multiple interface and associated with a multiple IP address. So this host with multi-homing can maintain multiple connections and multiple passes between itself and the corresponding host. So which means if one of the access link is broken during the mobility, the mobile host can still use the other connection with a high signal to noise ratio to keep on the communication, so the communication will not be affected. So this multi-homing using multiple access links is a very promising solution. And in the literature, there are already many multi-path or multi-link solutions at different layers. For instance, in the cellular system, a mobile user is allowed to connect to multiple base stations. So the cellular network can support a soft handoff using these multiple access links. However, this kind of multi-link in cellular network can only support a homogeneous system. All these base stations need to belong to the same service provider. Okay, and this may encounter some issue when we have a heterogeneous network. We need to do this handoff as well. And in the network layer, we see this multi-path routing is already quite possible, but the multi-path routing is mainly focused on improve reliability and load balancing inside of the network, not quite highly relevant to our mobility support. And we found that this managing this mobility at the transport layer is actually a good choice. For example, we have seen multi-path TCP can deliver data through multiple access links and access networks, which can provide seamless handover in both homogeneous and heterogeneous network. It can also support load balancing and bandwidth aggregation. However, in TCP, the three-way handshake is very problematic, which is very time-consuming, especially if we consider satellite network, which has very long round-trip time because the link distance is high. So on the other hand, we found Google has proposed a new transport layer protocol, QUIC, which is a QUIC UDP. QUIC supports multi-homing, but the original QUIC does not support to use multiple interfaces simultaneously. For this reason, recently we also see multi-path QUIC, MP QUIC has been developed. Compared to MP TCP, MP QUIC has quite a few advantages, particularly good for mobility support. First, it spends 0 round-trip time to restore an old connection. So this can largely reduce the delay for connection recovery. Second, it keeps the mobility support in mind and introduce connection ID rather than use IP address for maintain the connection. So when the mobile host move to a new places, even though it get a new IP address, but it can still use the ongoing connection without, so it does not need to reestablish connections. This is a quite advanced compared to TCP. Third, this MP Quick can be implemented at the application layer. So the kernel change is not needed, making it very easy to be deployed. Okay, and in LEO satellite networks, the very famous one is the Starlink, right? So if we use MP Quick, a ground station can access multiple satellites simultaneously and use multiple possible ground to satellite links to distribute packets. So even though some satellites may move away and the link broken, we still have another connection there to support a continuous transmission. Okay, we note the existing MP Quick solutions still encounter several issues, such as lack of coordination between the link layer and the transport layer, leading to performance degradation. That's the reason that we apply our new protocol architecture, the set architecture. Then we use PCA of each node to analyze the information from both the link layer and the transport layer, and to make good decisions accordingly. This approach has two benefits. First, the link condition, satellite link condition can guide the multipath control behaviors. For instance, we develop this mobility-aware congestion control and mobility-aware packet scheduling. Second, this multipath control can assist the link layer with things like admission control to guarantee the QoS requirements of current users. So we call this new protocol using our new architecture mobility-aware multipath quick protocol, or MM Quick for short. To facilitate research on MM Quick, our team developed a simulation test bed for MM Quick use NS3. So we, based on the existing Quick module in NS3, we implement the necessary new control blocks following our MM Quick design, include we define some new packet header and all the other necessary modulars to make it work. We apply the proposed MM Quick in the scenario of LEO satellite network. Well, here the mobility is due to the deterministic satellite movement. Taking advantage of this motion regularity, our MM Quick can predict how often handover will occur, and then we can set suitable timers to assist seamless handover. In addition, based on mobility-related channel estimation, MM Quick can decide how to schedule packets using different links and paths. Given this mobility information, the PCA in the ground station can estimate link data rate, handover time, etc., which can be applied to proactively control handover process and congestion control to enhance end-to-end performance. Okay. So we use NS3 to conduct the simulations, and here are the some results here. In these results, we compare the throughput of different protocols in these satellite LEO networks. We compare three protocols. The first one is the single path TCP associated with the advanced BBR congestion control algorithm. And the green line is the existing multi-path quick using the default OLIA congestion control. And the red line is for our proposed mobility-aware multi-path quick, which use PCA to do all this prediction and make a dynamic control. And we can have two observations. First, if we use single path TCP, although it uses very advanced BBR congestion control, the performance is still much poor than when we use multiple paths quick. And compared to the existing MP Quick, the proposed MM Quick actually can achieve much higher throughput particularly in some situations, the instantaneous throughput can even be doubled. So thanks to its capability of estimate the mobility and make intelligent decision about handover, about the scheduling, about congestion control. Okay, so quickly summarize. So to deal with this 6G challenge, we propose a new protocol architecture called self-evolving and transformative protocol architecture. It has the good feature of distributed coordination for QoS guarantee. It can support user-centric spectrum and mobility management, support adaptive starcast, and support ubiquitous intelligence. More importantly, this new architecture has just been developed, and there are many, many new open issues beckon further investigation. First, how to decompose the whole protocol stacks and build new control functions. And decomposing protocols in the existing layered architecture can be the starting point. Given the large number of existing protocols, it really requires a joint efforts from the research community to build the control function library by decomposing all these existing protocols. In addition, how to categorize the decomposed functions and build the general control functions with minimum overlapping with each other also require extensive further research. Second, for PCAs, the control process brings many open research issues. For instance, how to effectively discover the network environment. It needed to define what to monitor, how to measure, how frequently to explore, and what are the affordable costs. There is no one-size-fits-all answer to these questions. And the solutions should be customized based on network operation needs. In addition, given the historic data collected, the PCA may need to predict network dynamics, use advanced signal processing and learning tools, so on and so forth. And finally, this PCA needed to intelligently map the QoS requirement and the control functions accordingly, involving multi-objective optimization to minimize costs without compromising service quality in highly dynamic environments using advanced learning technologies. All these are critical for the research issue for the success of the proposed set protocol architecture. Okay, so if you're interested in this architecture, this one has already been accepted by IEEE Communication Magazine. It's available in IEEE Explore. And for the Quick protocols, we have 2 papers being published. One is in MSN 2021, it's an invited paper. Another one is accepted to be presented in GlobalCom this December. With that, I conclude my talk. So if you have any suggestion, comments, or question, I'll be happy to take. Thank you.
Thank you, ma'am. Thank you very much. Participants, any questions?
Good morning, ma'am.
Yes.
Yeah, good morning.
So it was a very good presentation. So thank you for imparting this knowledge to us. So what I have, one of the queries that now we know that 5G is going to be not just limited to the smartphones. It is going to have different market verticals. So similarly, as you quoted that 6G is going to have different applications with heterogeneous quality of service requirements. So how is it going to push the demand for the semiconductor process? Because currently we are going to have 7 nanometer chips and 5 nanometer chips. So we are already pushing the limits of physics. So how will this semiconductor processor demands be with respect to 6G when implemented in handsets or other devices?
Yeah, thank you for the question. Very good question. Although this CPU processor is not my research topics, but I agree with you that the 6G will become highly heterogeneous. And in many applications, probably the bottleneck is not the chips. So if you take a look, like many applications, the computing capability is not the bottleneck, but the network service is the bottleneck. So how can we have the ways to let distributed entities to exchange information in a very low latency and high reliability way. This is the challenge. So that's why my research is trying to address this challenge. So in current internet, we don't have suitable solution to support these levels of service guarantee. And this, I believe, is one bottleneck for 6G applications. So we want to develop new protocol architecture for that. Recall our internet has been here for 40 years, and the internet protocol architecture almost not changed because the IP is quite useful and quite agile to support all types of audio, video, text in applications for our human beings. But the 6G, the receiver will be beyond the human beings. Our sensors, our AI algorithms, our machines, our robots, UAVs, vehicles, they need to get the information and get a huge amount of information in real time. So how to have these types of networking service is, in my opinion, is a real challenge. Of course, the chips will keep on be advanced and moving forward generation by generation, well, which can make our smartphones more powerful, so on and so forth. But on the other hand, I believe even with the old technology chips, like 28 nano chips, there are still many robots or vehicles applications there. They are waiting for the network breakthroughs to connect them. That's my vision. Yeah, I'm not sure whether I answer your question.
Yes, ma'am, it answered. Thank you.
Any other questions? Any other questions from participants? Then put it in the chat box also if you have any mic issues. Okay, no questions, I guess.
And we can go for a group photo.
Yes, sir. Yes, sir. Yes, sir. Before that, we have one the releasing of members.
Yeah.
All of it.
So thank you, ma'am. Now I kindly request all
Yeah.
the dignitaries to release the inaugural video of the VTS Society of IEEE Madras Section. Please.
Mhm. Okay, yeah, thank you. Thank you for having me.
Hope my screen is visible, right?
Yes, yes, sir. Yes, sir. So this is our customized logo for Madras section. Yes, sir. The usual logo, we need to add that section name, so we have made it like this one. Sir, you can, sir. That's all, sir. Okay, we can take a group photo in the meantime. If possible, kindly switch on your camera. office bearers of this ETS Madras Section Chapter. Okay, sir. Next, any video? Chicken, sir. Now we can have a group pic. Please. Say 1, 2, 3. Adi. 1, 2, 3, sir.
This is the video we created for our logo launch and our office BRF team.
1 minute, sir. We will complete this photo session. Everyone.
Ma'am, can you able to hear me, ma'am?
Yes, sir.
Yes, ma'am. Shall we move on to the next agenda, ma'am?
Yes, sir. Yes, sir. Video. So share that video. That's over, no, sir.
Yes, ma'am. Over, ma'am. We'll
Okay.
present a small
Thanks.
token of gratitude to our speaker.
Yes, yes. Perfect, sir. Share that moment also.
I'm kindly accept it, ma'am.
Ma'am,
Thank
kindly
you so
accept.
much. Yeah, it's
So,
really nice. Yeah, thank you.
thank you for your wonderful presentation and gracing the occasion. Thank you very much.
Yeah, I really appreciate this. Thank you.
Thank you, sir, ma'am. Now I kindly invite Dr. Vijendra Babu, Secretary of PTA Society, IEEE Madras Section, to deliver the word of thanks. Please, sir.
Good morning to all of you. Am I audible?
Yes, sir.
Yes, madam. Thank you. Madam, I place my sincere thanks to the chief guest of today's event, Dr. Lin Cai, Professor, Department of Electrical and Computer Engineering, IEEE VTS Board of Governors, 2019-2024 University of Victoria, Canada, for delivering the wonderful technical talk on self-evolving and transformative protocol architecture for 6G. Since we place a hearty thanks, madam, on behalf of our IEEE Madras Section and IEEE Vehicular Technology Society of Madras Section for you to be inaugurating a society. We hope from this point we will be making wonders with all the support of all the members and experienced members of Board of Governors across the globe. I hope the support of these members will take it to the next level, as this is going to be one of the leading technology in current days to come. As on your session, it was very useful that we are just because from Indian point of view, we will be just implementing, experiencing the 5G very shortly for last 1 month from selected cities. Maybe in one more year, we'll be experiencing the whole exploiting situation of 5G. But now we are very interested to look about what is going to be 6G, what are the challenges. As we rightly said about AR, VR, hologram, which takes care of more amount of data. So as rightly you said about, I was covered about all those things, and very significant parameter that's about human cyber physical interaction, which is a need of the hour, I think so. So once the evaluation of Internet of Things and all those things and utilization of higher data rates, in this automation, Industry 4.0, and the next point, which was very interesting, that 6G to be intelligent. So as we have covered everything, it's about the challenges and about the need for self-evolving. So justification for getting on into the self-evolving and transformative with respect to the protocol function or protocol control agent. It was a new avenue for all of us to look into the next avenues of research for faculty members and students to get over it. And you have touched about the used cases about the packet lane delivery, mobile aware multipath for satellite networks too. We were very much thrilled about the session, madam. We hope we will be having a collaboration with you in future avenues from various institutions across India for you as we have kicked the first step rightly to it. And I once again place our sincere thanks for your presence and making this a very grand success. And I also thank Dr. K. Porkumaran, Chairman, IEEE Madras Section, for permitting us and allowing us and to conduct this event in a very grand manner and very grand and professional manner. Thank you, Chairman Sir, for IEEE Madras Section, and all the executive members for the support for making this to happen on this very auspicious day. As a Thursday, we say it's a very auspicious day also for us. And I place my sincere thanks to all the participants across India, faculty members, research scholars, industry members, and students, members of participating for making to know what is about Vehicular Technology Society, what it is going to be look over it, and sincere thanks to it. And kindly be a member if you are not member of it and utilize this opportunity. Many opportunities are evolving for getting the grants, getting the scholarships, like in support of the Lin Cai madam and all those things. I place my sincere thanks to all my executive committee members. Special thanks to our Dr. Vrinda madam, the chairman, for making this initiation, and all these vice chairman, secretary, treasurer, student members for making this, and the team members who have been making this event to make grand success, like unveiling this logo and all those things. And at last, with the support of all the IEEE members of Madras Section and Almighty God, I thanks for the opportunity given. Thank you.
Thank you, ma'am. On behalf of the society, I thank you all the members who joined this meeting. Thank you all.
Yeah.
Kindly
Thank you
fill
all.
the feedback form.
Yeah.
To receive the certificate. Thank you, ma'am.
Thank you all.
Bye.
Yeah, thank you, Professor. Thanks all. Thanks. to all.
Thank you. Thank
We'll
you.
take
Thank
one
you for
group
having
picture,
me here.
ma'am.
Any Madras Section executive members join this meeting, ma'am, to listen your talk. Thank you, Arun sir.
Thank you.
Yes. Many members
Thank
joined.
you, madam.
Nityavati madam, thank you very much for joining with us.
It's okay.
Yeah.
Ratnavil sir, Dr. Ratnavil sir, thank you very much for joining the meeting.